All right, so now we'll take a look at basically what some of these hypothesis tests look like when we actually carry them out in R or in our software and things like that. Okay, so first we will take a look at this one data set from the textbook Handbook of Statistical Analyses Using R. Okay. Let me, do I have the textbook downloaded here? Okay, so Handbook of Statistical Analyses using R, and, oh dear, I already forgot what I was saying. I need to get which chapter is it? It's chapter 3. Okay. All right, so we're gonna skip to chapter 3. I think. Let's try around there. Oh. Okay. So here's the data that appears. Okay. And what we see here is this data comes from the 1970s, okay? But I guess in Australia, in the 1970s, they said, we are going to switch to the metric system, okay? So they keep talking about doing this in the US, but we never do this, right? I don't think it's ever gonna happen, right? So where it's like the US and Liberia, I don't know, and Burma, I think are the only, no, Myanmar, wait, I forget which name it is. Okay, but are they like the only 3 places in the world that use the imperial system? Everyone else kind of uses metric. Okay, I mean Canada is a little bit like a mix, but so anyway, so in Australia they switched from imperial to metric, and this is like new, and they just wanted to know like, how good are you at estimating things, right? So I think in our brains, because if you grew up in the United States, you're very accustomed to the metric system, right? And if I tell you that somebody is 5 feet 10, you can imagine how tall they are. You can picture them in your brain. And if I tell you they're 5 foot 11 and 5 foot 5, like you can picture these things, right? But if you are new to the United States, right, and you're accustomed to the metric system, all of these things, these just sound like gibberish, right? And on the other hand, just depending on what system you're accustomed to, you can probably, ballpark, So if you, someone who grew up in the U.S., like, what would you guess was the width of this room in feet?
50 feet wide? 28.
28. Okay. All right. Okay, all right. Okay, so we're getting estimates all over the place, but that's okay. All right, right. But then if I told you, all right, give me your guess in meters, right? And then now you're like, okay, well, I'm gonna do this and I guess divide by 3, but maybe round down or something, or I don't know if you're from India, so I'm assuming you. But not to say like you have to guess, but
10 meters.
10 meters. Okay, all right. So maybe something around there, right? Okay. So anyway, this is basically the problem that they did, and they asked different students, and they said, make your guess in meters, and then make your guess in feet. Okay. And we want to know, is there basically a difference in? Well, I guess we'll look at the mean and the kind of the difference in their guesses that they've done, okay? And so here, if we wanted to, so the data that we have, one variable is numeric, okay? And then one variable is categorical. We got a categorical variable with 2 values. That is, one is the guess was made in meters, and the other is that the guess was made in feet. And then the other is numeric, which is the actual guess, okay? And all the observations are independent. So here we can do either a 2-sample t-test, which I hope you are all familiar with, but we'll go through it here, okay? And then so you have the Welch and the students 2-sample t-test. You guys know the difference between these two? This is like trivia, stats trivia. Okay, but basically we just call these the t-test, and they're like the same thing. Probably the difference that you guys know maybe is when they covered the t-test in intro stats, did they talk about pooling your variances or leaving your variances unpooled? Okay, that's the difference. Okay, so okay, but even if you don't remember that, probably the most common thing is the Welch two-sample t-test, and then but then students t-test is also common. Okay, and then the other is the Wilcoxon rank sum test, and I don't know if you guys ever covered the Wilcoxon rank sum test. Is this like super foreign and new? The non-parametric version of the t-test? Okay, all right, well, we'll talk about all this. Okay, so we're going to start with the t-test, okay? So when we talk about the t-test, we basically have one group has a mean and the other group has a mean, and we're trying to compare means, right? So this, do cats weigh more than, this is a bad example, okay. I guess maybe a certain breed of dog, right? Like, do cats weigh more than Chihuahuas or something like that, right? And so you take, one group has an average and the other group has an average, and you're comparing the averages of these two things, right? And so here we want to know, is the guess made in feet, does that have a different mean from the guess made in meters, okay? The only problem there is that obviously the number, like, we can't compare the numbers directly because the meters guesses are going to be much smaller than the feet guesses. So so we're going to have to convert these, okay? So we're going to just, we do a few things in R, okay? So the data, like, there's a few ways to get data into R. One is like you have an Excel sheet or a CSV and you load it in. And others, like there's packages where the data is already in there, okay? And so this one, so most books that say we use R will have an associated package, okay? It's like almost a requirement. If you're gonna write a book about R, you need to have a package that goes along with it, okay? And so this one is Handbook of Statistical Analysis using R, second edition. And so there's a package called HSAUR2, and so you need to install this package onto your R program, okay? And once you have that loaded, you can load up the data by using the command data, all right? And so this loads this up and we get something called a promise, but it's basically, if I click, as soon as I click it, it becomes the room with data set, right? So here it is, and we have a total of 113 observations, 44 of them are done in meters, and this is Australian, so they even spell meters the funny way, and the other is in feet, okay? And so so this is what we have, and we can just kind of take a peek at the first first 4 rows and last 4 rows, and indeed we see the first 4 are done in meters and the last 4 are done in feet. And so here I'm going to create, I'm going to take the meters and I'm going to multiply them by 3.28, okay? And so here I'm going to just create a column of values that will either be 1 or 3.28. And so basically, if we're going to convert everything into feet, okay? So if it's meters, I'm going to take the number and multiply it by 3.828. That's the conversion factor. And if it's feet, I'm going to just leave it as it is, so I'm going to just multiply it by 1. Okay, so I use this function if else, and if I say if else, if this column says feet, the conversion factor is 1, and if it's not feet, if it's something else, the conversion factor is 3.28, okay? So we'll go ahead and do this convert. So convert will be a vector of length 113, and basically the first few values will be 3.28, the next values will be 1.0, okay? And then, and so I'm going to create a new kind of vector of values, and I'm going to take the width column, which has the values in meters and feet, and I'm going to multiply everything by the conversion factor, okay? And so if I take the room width, $width, okay? So the beauty of R is that it will do vector-wise multiplication. So it's going to take this 8 and multiply it by 3.28, take the 9, multiply it by 3.28, and just go element-wise until it gets to a certain point. Well, I mean, till all of this in this one, that's 94, it's going to multiply by 1, okay? And to get this back into my table, I'm going to just bind that column using cbind, column binding. Take the room width entire data set and bind the column onto it, okay? Oops, did I not run this correctly? Okay, so there we go. And so now I have the, looking at the first 4 rows in meters, but after converted, it's 26.24, and then feet, we leave it at 70.0. Right. Okay, and then so now we can go on and do some work here, okay? And we can calculate summary statistics. Okay, so if you're new to R, this is where we start doing some stuff. Have you guys, I guess even for those of you who are familiar with R, have you used something called dplyr? Dplyr, okay. And wait, did you guys have the R boot camp also? Or was that? No.
It's part of our math camp.
Oh, okay, your math camp. Okay, okay. Did they talk about dplyr at all in there?
No, it's
okay.
actually data structures.
Okay, data structures. Okay, well that's important. That is important. Okay, you get. So you learned about vectors, matrices, lists,
Arrays.
Data frames. Okay, yeah. Okay. All right. Well, there's something called the tidyverse. Okay, and it's a bunch of packages developed by this guy Hadley Wickham, who's like the master of R programming. Okay, he really truly has done so much for R as a data analysis, data science tool, and I think part of the reason why R is popular is because of the packages he's produced. He works for RStudio, which it makes this nice graphic interface that I recommend to everybody. And so anyway, you can calculate these summary statistics. Okay, so here all I want is I want to calculate some summary stats, and so there's a function in R, like if I take, let me just call x the values 1 through 10, so x is that, I can just say summary x, and it's going to tell me a bunch of numbers. It's going to give me the min, the median, the max, the mean, the first quartile and third quartile, and stuff like that. Okay, so it gives you basically your 5-number summary plus the mean. Okay, and you can use a function called tapply. Tapply, it says basically apply something, make a table, okay? And so here we're going to apply to the estimate column, which is, again, this column of values. We want to apply the function summary to it, but it's going to be kind of grouped up by the unit, the feet or the meters, okay? So if I do this, tapply produces this, and it says for feet, here are the summary stats, and for meters, here are the summary stats, okay? So we see that the mean estimate in feet is 43.7, and the mean estimate in meters is 52.55, okay? Whereas, and then we can also ask for the standard deviation, and it produces this, this table for us, okay? Personally, I think I prefer dplyr. This, at first, it looks like a little bit more work, okay? But I find it easy to interpret and understand, okay? So here it says I'm taking the data room width. I'm going to create groups based on the unit. So here I'm going to create groups based on whether it's feet or meters, okay? And this thing, this percent greater than percent, is called a pipe, which says take this thing and pass it on to the next function, okay? So we're going to do room width, we're going to create groups, and then we're going to pass that on to the summarize function. And the summarize function will create summaries for each grouping. Okay, in this case, we're going to have a grouping for feet and a grouping for meters, right? And so the things we're going to calculate are going to be the count, the n, the mean, which is going to be the mean of the column estimate, the median, which will be the median of the estimate. So on the left-hand side, before the equals is just the title. Okay, so this is arbitrary. This is not, whatever I write here doesn't actually matter. I can call it whatever I want. And the thing on the right is the R function that's being performed. Okay, so these names actually matter. Okay, the median, SD, min, and max. Okay, and we want these things. And so if I run this, it's going to produce a nice little table here. And it says for feet, there's 69 values. Here's the mean, 43.695. The median is this and that. Okay, and these indeed match exactly what we found using the t-apply statistics. Okay, I know I did this a little bit quickly. Okay, and again, this is all kind of wrapped up and kind of just getting familiar with this. There's an excellent book on using the tidyverse packages. Okay, and this is it's R for Data Science. Written by Hadley Wickham and Garrett Goldman. They are, they both work for RStudio, okay, and teaching these things. And you can buy the book, but it's here. The entire book is available just on their, just on this webpage, okay. The entire text of the book is available here. It's just only if you want a printed copy do you have to pay for it, okay. So this is all in there, and I recommend looking at chapter 5, okay? And this will get through some of this stuff, okay? I mean, you can look at the other chapters as well. Okay, so so here we just want to, we're like, if we compare means, is 43.7, is that significantly different from 52.5, okay? Could this difference of 43.7 to 52.5, could that be explained from just the random process, right? Like if we just randomly reassigned who is going to say feet or meters or something, like is it possible to still get this kind of discrepancy, of difference of around I guess 9 feet? Okay, is it possible to get that? Or is this difference can that only be explained by the fact that some used meters and some used feet, okay? Maybe to kind of get a better idea, we can create a box plot, okay? And so the key part here is just box plot estimate tilde unit, okay? Everything else is just options to kind of make it prettier, okay? But here we want to use, look at the estimate variable, which is the numeric variable, explained by the categorical variable unit. Okay, so if I go ahead and run that, then we get this, okay? And this kind of shows a little bit more clearly the difference between medians, and also it gives us a sense of the spread of the other values that appear in the data, okay? And so, so you know, an interesting thing is that when we look at the feet, most of the values are kind of down here, and if we look at meters, there's definitely, it looks like the values get kind of inflated, okay? And I think probably, this is my guess, right? I look at this room, I think, okay, maybe it's like 30 feet, okay, or something like that. And so if you told me, so here, you know, I grew up in America, so I'm accustomed to using feet, not accustomed to using meters, right? So this is my process. This is my hype. Like, I'm just guessing what happened, right? So I'm like, okay, okay, maybe the room's 30 feet wide, right? But then I'm like, okay, well, if you ask me what the answer is in meters, the conversion factor I'm doing is I'm taking my thing in feet and dividing by 3, right? So I'm going to go from 30 feet down to 10 meters or something. But this is probably wrong, right? Because the conversion factor is actually 3.28. So it's going to be, it's actually smaller than 10. And I don't know what 30 divided. I can't do 30 divided by 3.28. What is that? Is that like 9? Is that something even smaller? It's a tad over 9, 9.14 or something, right? Okay, so anyway, I think if you take that and you compound the fact that, maybe people just aren't very good at guessing the thing, I don't know, I wonder if this is like, if the difference between 3 and 3.28 is around 10%. If we look at our summary stats, are the meter numbers about 10% bigger? No, it's even more. But yeah, we're getting quite a difference. If you look at the standard deviation, it's quite different as well. So it's kind of interesting, right? So anyway, we can do the rather than just looking at the pictures and going with our gut feelings and saying it looks different, we can carry this out with a statistical test, right? And so kind of the basic one is the t-test, right? We've got 2 samples, all right? And we want to compare these. So when you do students 2-sample t-test, this assumes that both groups have the same variance. All right, so we're assuming that the variance in the meters group is equal to the variance in the feet group. Okay. The other assumption here is that the sampling distribution of the mean follows the normal distribution. Okay, and so this is probably a safe assumption. Okay, as long as we've got like a big enough sample. We can kind of assume the central limit theorem holds, and if the central limit theorem holds, then the sampling distribution does indeed follow the normal distribution. Okay. And so we set these up. The null hypothesis will be that the 2 groups, their respective populations, have this equal means, and the alternative is that they're different, right? So here, to conduct this in R, we just run t.test, and we say we're looking at the numeric variable estimate as explained by unit. Okay, our data is coming from the room width data set. We say variance dot equal, that we give that the option true. And then for alternative, we'll say 2-sided. The default value is 2-sided anyway, so you can actually leave that off. But and so we get the 2-sample t-test. All right, so the null is that the difference in means is equal to 0, and that here the alternative is that the difference is not equal to 0. And we get a p-value of 0.01. Okay, so a p-value of around 1%, and we say that this difference, okay, we got a difference, between 52.55, 53.69. That difference cannot be explained by randomness alone. Okay, so something else is going on. And for yes, we're going to assume that which group that they were in, whether they had to make a guess by feet or meters, is related to the fact that their guesses are different. Okay? Is that all right? Any questions on this? Okay. Are there any objections to using the t-test? The 2-sample t-test? Okay. Well, the big assumption here is that both groups have the same variance. And when we looked at our summary statistics, that doesn't seem to be true, right? Here I've got 12.5 and 23.43, right? So it seems like, okay, maybe I shouldn't use this thing, right? So one nice thing about the 2-sample t-test is that the degrees of freedom is easy to calculate. Okay, you just do n minus 2, right? You got it's technically n1 plus n2 minus 2. Okay. So if you don't want to say that the 2 groups have the same variance, you can do the Welch test. Okay. So the Welch test basically says the variances are different. Okay. Also depends on the central limit theorem. And this is what R does by default, okay? So when you call t.test, it's going to run a Welch test by default, okay? So here the command is even shorter. We just do estimate tilde unit to kind of say, take our numeric value as explained by the grouping variable unit, okay? The data stored in the room width data. Okay, and when we run that, we get a p-value of around 2.5%, 0.025. Okay. And now our degrees of freedom is this weird number, 58.788, which is found, let's look up Welch test. So if we look at Welch's t-test on Wikipedia, so basically is an adaptation of students' t-test is more reliable when the two samples have unequal variance, okay? And this is kind of how it is. I don't know if you guys recall your intro stats class, how long ago that was or whatever, but you know, you have x bar 1 minus x bar 2 divided by the standard error, which was s1 squared over n1 plus s2 squared over n2. Okay, yeah.
Is there a test we can run to determine if the variances are close enough together that we should consider them the same?
Yeah. So now this is like test inception. What is it called? Fisher's test for equal variance. Let me just see. All right, test for equal variance. The Levine test. I was thinking the F test. The F test of equal variances. The Levine test. I don't know what this is. We're gonna have to read this. Levine 1960 is used to test if K samples have equal variances. Okay, so it's like a generalization of this. Okay, so you have different, yes, there are tests, okay? And I don't even try to pretend that I know what tests are out there, okay? A lot of times I'm just like, oh, I should test if this is true. And I just type into Google and I'm like, how to test if this and this is this and this, right? And then it'll say, oh, Levine test or this test. And you're just like, okay, let me read up on this. Let me go to the Wikipedia page. Let me see. And then so you figure this out and you're like, okay, this sounds like what I want to do. The next thing I do is Levine test in R. And then I try to find if there's something that did this, and then I read the documentation for that, and then I try it out. This is, there's just like all sorts of stuff. Probably a lot of these things will have like a research paper associated with it. And if you want to be good, you should probably read at least the abstract of that thing to make sure that the scenario that the author had in mind resembles the scenario that you have, that the data, not that the source of data matters, but just that the kind of situation of the data that they're working with matters. My honest confession, though, is as a teacher, I only use a handful of tests, and a lot of my things I'm like, okay, t-tests and chi-square tests and this, there's really only like a handful of things that these are kind of your like first bread and butter cuts, and then maybe you're like, okay, this is a slightly weird situation that I need to check out and stuff. But yeah, there's also like what's an outlier, right? There's all sorts of tests for that. Like, is my data normal? And then you got all sorts of tests for that, and you kind of have like standard ones like the Shapiro-Wilk test and KS test. Yeah, there's all sorts of stuff. But yeah, this covers a lot of good stuff in this textbook, right? So Introductory Statistics with R and a Handbook for Statistical Analyses in R covers kind of a fairly wide breadth of these things. But yeah, a lot of times I go to Google and I say how to test for this, and then I find out what test it is, and I see if somebody has already implemented it in R for me, or something, okay? That's what it looks like, okay? Just like, and I look up the most basic things as well. You think after X amount of years you would remember how to do all of these things, but I'm constantly reading the documentation for exactly how to set up the function, and that's totally normal and totally good. Okay, so anyway, we do the Welch 2-sample t-test. We get a p-value a little bit bigger, around 2.5%, which is still small enough. If we're using alpha equal to 0.05, we would still reject the null hypothesis and conclude that the two groups have different means. Okay. Okay, so here's my commentary on the differences between the t-test and Welch test. Okay. So in general, the Welch test will have fewer degrees of freedom than the t-test, which ends up giving to a wider distribution and smaller or larger p-values and things like that, okay? If you're not sure whether you should assume equal variances or unequal variances, the recommendation is assume unequal variances, okay? If you assume that they are unequal and they turn out to be equal, okay, the difference between one p-value and the other is like, it doesn't really matter, okay? It hardly makes a difference in the conclusion you're gonna make, okay? But the reverse can't be, is not true, right? If you assumed they were equal but they turned out to be unequal, the p-values can differ quite dramatically, right? And we see that a little bit. The p-value for the unequal thing, which is probably the correct version, had a p-value about twice as big as the equal version thing, okay? All right, and then the other test that we can apply in this situation is the Wilcoxon rank sum test. This is the non-parametric test that can be used in situations that are similar to students' t-test. So the situation we have here is we've got two groups. We've got a grouping variable that separates the data into two groups. Here it was meters versus feet, but it could be cats versus chihuahuas. It could be this political party versus this political party. And then the other variable is numeric, okay? The weight of the animal, the size of the estimation, some numeric value, okay? So it's not like you can't be dealing with a categorical thing, okay? So we've got one variable that's categorical, and then the other variable is numeric, and you're trying to see if there's a difference in kind of like the average value of the numeric thing, okay? So in the t-test, we're comparing means. So with the Wilcoxon rank sum test, it's a little bit strange, but we're comparing, I guess, maybe central tendencies, okay? It's under a family of what we call non-parametric tests. Non-parametric means we don't like to talk about parameters like the mean. We don't like to use these summary values like the mean or the variance or things like that, okay? So the t-tests, the parametric ones, they depend on the central limit theorem, which has normal distribution and a mean and things like that. The non-parametric tests say, I don't want to make assumptions about the sampling distribution. I'm not comfortable assuming that the sampling distribution is normally distributed, okay? So I don't know if I wrote basically the one-line version of that, okay? The key difference is that it does not make distributional assumptions about the sampling distribution, okay? So we're not going to assume that it's normal. The sampling distribution is normal. And when should we not assume that the sampling distribution is normal?
With small samples?
With small samples, right? So earlier we said if your sample is bigger than 30, for most cases, your sampling distribution will look normal or something like that, right? But if you have a small sample, maybe the sampling distribution is not normal, right? And then, so the other part is, so if you have a small sample, maybe you don't want to do this, okay? Or if you have, if there's big outliers, right? So if you have big outliers in your data, okay? So if you're looking at your data and one thing is like 10 times bigger than another data point, you might say, okay, maybe the population is really skewed and a sample of 30 still isn't big enough or something, okay? And so, depending on what you see, you might be in a situation where you don't want to make this assumption, okay? Oh, so I guess that's what I wrote here, okay? Practically speaking, if you're relatively small sample, I guess I wrote 25 here. Okay, well, I hope that's all right. I know we just said 30, but here I have 25. Okay, or there's some large outliers, okay? and it looks just like, it's like I took the thing that said t.test and I just changed t to Wilcox, okay? All right, and that's just a thing, okay? And then so now we get a p-value of around 3%, 0.028, and here the alternative hypothesis says true location shift is not equal to 0. It doesn't even say something about the mean or the difference in means or something like that. We're just avoiding any of these parametric words, okay? But we carry this out using a Wilcoxon test. If you can use a parametric test, I would recommend you that you can, okay? Only use a non-parametric test if you're really uncomfortable about the assumptions behind a parametric test. In general, a non-parametric test is going to be less powerful than their parametric counterpart. A non-parametric test makes fewer assumptions, and because you're making fewer assumptions, it takes a lot more to make a conclusion, okay? And this is true about all of life, right? All of life, we're constantly making assumptions about people, right? You look at someone and you just automatically start assuming things about them. And this is probably, this is how we just function. Not that to say that this is good or bad, okay? So if you assume something about someone, it just takes a little bit of like one action, and you're just going to say like, oh, of course that they would do that, right? On the other hand, if you make no assumptions about anybody, it takes a lot more interactions for you to come to some kind of conclusion about the person. And similarly, a parametric test makes assumptions about the shape of the sampling distribution. It assumes it's got some parametric form like the normal distribution or something like that. And so as far as the data goes, it doesn't take much to reach some kind of significant p-value. On the other hand, a non-parametric test requires a lot more data in general, more data in order to come to the same conclusion because it's making fewer assumptions, okay? Just like life, when you make assumptions, it can get you into trouble, right? It can get you into trouble. So, if your assumptions turn out to be wrong, right? So, for example, maybe you're out on a first date with somebody, and then the person you're with is rude to the waiter, all right? And so that interaction suddenly clouds your picture of who this is, right? You're like, oh, you were rude to the waiter. Now I'm judging you, and this is a red flag, and I don't ever want to go out on another date with you. And maybe that's fine, okay? But that assumption where you're making a quick judgment based on one interaction that this person had with the waiter or whatever, maybe it was wrong, and maybe you missed out on a truly wonderful person who just had a rough day that day, or so, I don't know, whatever. Not to make excuses for someone's behavior, but we're often hasty to come to judgments about things that maybe we feel like, oh yeah, I don't want to. If someone's rude to the waiter, then blah 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 about the rest of their life, and now we're saying like, oh, they were probably had parents who taught them all these wrong things in their childhood, and then later on you see them and they post, I don't know, you're stalking them on, I'm just making up stuff, right? And then you're like, oh, of course, this person is going to say something. Of course you're going to post that on the internet, right? Like, who knows? Okay. We're going to keep going on. Okay, so the next data set that appears in this Handbook of Statistical Analysis is this water data, okay? The waves data, not the water data, the waves data. Okay, so I don't even know this. This data set comes from 1994, and it says they were looking at some device that's going to generate electricity from wave powers from the ocean, right? They did this study in 94. Apparently it didn't catch on because I don't hear about wave power energy farms, right? But we got offshore wind energy farms, so something happened, right? Okay, but anyway, they did this, and they're looking at different methods. So we're looking at the bending stress as measured by the root mean squared bending moment in Newton meters. I don't even know what that means, okay? But we recorded this between method 1 and method 2, okay? But here's the important thing. It says the wave tank could simulate a wide range of sea states, and the model system was subjected to the same sample of sea states with each of the 2 mooring methods, okay? One which was considerably cheaper than the other. So it wasn't that we did one set of experiments with one method and then we did another set, okay? We said, all right, let's have this wave tank simulate this condition, and we're going to see how method 1 performs, and under the same conditions, let's check out method 2, okay? And then we're going to try something else, and we're going to see this is how method 1 performs, and this is how method 2 performs. So we're subjecting our 2 methods to the same set of conditions, okay? So each of these things are in a situation that we call a paired data situation. And what we want to know is if we look at how the 2 methods performed under scenario 1, and how the 2 methods performed under scenario 2 and scenario 3 and so on and so forth, is it consistent that method 1 consistently outperforms method 2 or something like that, okay? We're not treating these as just random trials over here and random trials here. We have what we call paired data, okay? And this is often useful when you want to know if something is effective and the different kind of starting conditions have played a bunch of different roles, right? So you might be interested in like I don't know if some medical treatment is effective at something, but if your original sample is small, maybe the variation in just this one sample is so great and the variation in the other sample is so great that maybe the treatment is actually effective, but because you're treating these the variation that is kind of inherent to these different samples is so great that the difference is kind of undetected, okay? And so paired data allows us to say, okay, we tried this treatment on this condition, and we tried the other treatment basically on the same condition, maybe either on the same person or like twins or something, and then if it's consistently that this one is different from this one, then we can come to some kind of conclusion, right? So this is a situation where we have paired, okay? Each observation in one column is paired or matched with an observation in the other column, okay? And then so you have the student's paired t-test, okay? And then you have basically the Wilcoxon-Sainz rank test, which is basically the non-parametric version of this. And so I'm going to just kind of skip ahead. And so, there's kind of a setup. Basically what you do is you take the difference, you take one column and the second column, and you just subtract one from the other, okay? And you get the difference column. And we can plot this. And so here, if there was truly no difference, we would expect that difference to be right around 0. And we're consistently seeing method 1, I don't know about consistently, but over half of them have a positive difference. Method 1 is greater than method 2, okay? And then to kind of see if there's, and so we do see one dot here, which says it's an outlier, so maybe we don't want to assume normality or something. And so we kind of plot this and we create a QQ plot, and I don't know, it's hard to say, right? When you look at QQ plots, ideally all the dots follow the line, and we get a little bit of deviation from the line, and it's hard to say. Nothing seems super extreme, so maybe it's okay to kind of continue on, okay? And so here, we've got 2 columns of data. We're going to just do t-test, okay? And we can just either do the t-test on the column difference, or you can just do the 2 columns and say paired equals true. And these are going to give us the exact same results, okay? So if we do it on the column difference, we get 0.3797. And if I do the paired t-test with the 2 things with paired, it gives me 0.3797 as well, okay? The Wilcoxon sign rank test is the non-parametric version. We tell it, basically we just do Wilcox test, and we say paired equals true. And again, basically I've done the same thing. One is I've calculated the column for the difference, or I could just treat the 2 columns separately, and internally R will calculate the column difference for us and deal with this, okay? And we get the same p-values in both of these cases. Yes?
So, quick question. When you have a paired t-test, is it
Yeah.
taking the difference and seeing if the mean of that difference is different from 0?
Yes.
Okay.
Yeah,
Got it.
so paired t-test is basically, I mean, so you can manually do this. You can take the difference manually and then compare that column of differences to 0, okay? And that's, or you can just give the 2 columns and tell R to do it, and that's what it's going to do. It's going to take the differences and just see, is that difference equal to 0? Because if the null hypothesis were true, we would expect the difference between columns to be right around 0, and if it's not, it's going to be different from 0, and that's what we have. Okay, and the last one, we are going to look, I guess just in a couple of minutes here, at this water hardness data, okay? And I forget the exact details of this data set. Okay, so we looked at the mortality. I don't remember. Okay, so we're looking at mortality and water hardness for all of these different locations in England and Wales. Okay. So we're just trying to see, is there a relationship between the hardness of the water and these mortality rates? I mean, it's a little bit morbid, but we want to know, is there, so we have two numeric variables, 2 columns, they're numeric variables, okay? And so when, kind of to see if there's a relationship between 2 numeric variables, kind of the go-to statistic is correlation, right? So you're just going to calculate, and when we talk correlation, the kind of the one that we immediately think of is going to be Pearson's correlation. When you just hear someone say correlation, they're usually talking about Pearson's correlation. But then there's other correlation. There's like Spearman's correlation, which is based on rankings and not the actual value, and Kendall's correlation, I forget exactly how that's calculated. Okay, so anyway, here are the values. Okay, this is the scatter plot that we have, and so if anything, it looks like there's negative correlation, where areas where there's high water hardness seem to have lower mortality, which I guess, yeah, okay, so that's what it appears, and we want to know, okay, is this correlation significant? So we got negative 0.65, okay, is that significant, or could we get something like this by randomness, right? So if I just took a whole bunch of darts and I just threw them at the wall, okay, is it possible that the darts that end up on the wall to have a correlation of negative 0.65, right? If I just take a bunch of darts and I throw it at the wall, I would just expect this big mess of cloud of points, overall correlation of 0, but of course, not necessarily exactly 0. Is it possible to get something like negative 0.65 just from random throwing of darts, okay? All right, so there's like a bunch of tests that you can do, and I just linked to the Wikipedia page. But in R, it's really simple. All you just do is say, I want the correlation test, core.test. By default, it's going to do Pearson's correlation. and then you can change it up to Spearman or Kendall's correlation. And to be honest, I don't remember what Kendall's correlation is. Kendall's rank correlation tau. Okay, so basically the conclusion is you get this p-value on the order of 10 to the negative 8. Okay, so basically it says if you take a whole bunch of darts and you throw them at the wall, it's like never going to happen where you're going to get a correlation of negative 0.65. Okay, that's just like, it looks like a mess here, but you're never going to get something where the correlation, like if you calculate the correlation, it's like never going to happen where the correlation ends up being negative 0.65 just from random chance if you throw all of these darts at the wall. Okay, with this many dots. Okay, maybe with a fewer number of darts, like if you throw 4, sure, maybe you get a correlation of negative 0.65. That's easy to happen. But we've got like 100 of these things, and then for a correlation of negative 0.65 is not going to happen. Okay, and so that's what we have, the correlation test, and we have that there. Is that good? I feel all right. Okay, all right. Well, that's our first class. Kind of just a review. Maybe not a review for some of you, of kind of a bunch of concepts in intro stats, and next week we'll start looking at some randomization stuff, and we'll have that. Okay, I've got some stuff posted online, and then again, my encouragement is for you to kind of form study groups and work together, and help each other, but of course don't just copy each other's homework. Please don't do that. So, all right, looking forward to a good quarter with you guys.
Thank you.
Have a good night. Yeah.